Hello. I'd like to get another recording in. It could even be the last one of the semester for data structures. I'm going to be talking about several things with graphs. The last time I did a video, I talked about two methods to find a path between two nodes in a graph. They were breadth first and depth first. I said there were three. The third one is the one that gets us the shortest path, and it's called the shortest path first. It's similar to an algorithm you might have seen called Dijkstra's shortest path algorithm, but Dijkstra goes from one node to every other node. We only have one node to one other node. I'm going to illustrate this by this example, which I think I set up before. This is a weighted digraph. That is, there are distances, numbers on each of the arcs. So from Boston to Chicago is 990 miles. I think I got that from either an atlas or someplace on the web. Boston to Hartford, 101. Boston to Providence, 49, and so on and so on. What I want to know is, what is the shortest path between Boston and New Orleans? Now we have choices of paths. We could go Boston, Miami, New Orleans. We could go Boston, New York, Pittsburgh, New Orleans. We could go Boston, New York, Miami, New Orleans. I think I said that. We could even go around in circles. We could go Boston, New York, Miami, New York, Pittsburgh, New York, Miami, New Orleans, but that would be silly. So the question is, how do we do this? Well, in breadth first and depth first, we were talking about a queue and another structure to keep track of where we had been, where we had checked already. We're going to do the same thing here. The difference is the queue will be closer to a priority queue than a queue as we did in the last one. And the priority is going to be, we want the shortest path we have found so far on the top of the queue. That's the next one we're going to look at. So the way this works is we find the shortest path that we have in one heap from Boston. So that's going to be Providence. Now, we now look at paths coming from Providence. There won't be any. The next one's going to be Hartford. There won't be any there. The next one's going to be New York. There are going to be paths leading out of there. And some of them are going to be longer than the others. The object is that we're going to search every path until we reach one from New Orleans that is shorter than any other path to anywhere that we know. Because if we only have longer paths in the queue, then there's no possibility that we can make a shorter path to New Orleans. So the way we would do this is we'd start by putting together the first possibility we have out of Boston. And the queue now has the path, the last point of it, like Miami, and how long that path is. So I ordered these, shortest one on the right, and I'm looking at the right as the top of the queue. So now what I do is I take an element, I take that element off the queue. There's no children, so nothing happens except I put Providence in the done pot. Hartford is the same way. There's no possibilities, no changes, so Hartford is done. Now I come to New York. New York has paths to Pittsburgh and a path to I think it has a path also to Miami. So what I looked at now is the New York to Pittsburgh path is 585. That is smaller than the Chicago path. So I'm going to go to that path before looking at Chicago. Now I have New York, Pittsburgh, New Orleans, and it looks like we should be there. We have a path to New Orleans. However, we have two shorter paths in the system. And we have to check to see if any of those will expand to get us to New Orleans in less than 1679.1. So we look at that path to Chicago, nothing new. We still have this path to Miami. Well, Miami has a New Orleans path, but if we put it all together, it's 2359.2. There's no way we're taking that path. So there's no new shortest path to put on the queue. The queue has now one item in it, and that's the shortest path. Now that's a pretty reasonable algorithm to talk about, but it takes a lot of little details. You have to keep track of the paths, and you have to keep the queue in order. It's basically a priority queue again, where the priority is the shortest path is the most prior, has the most priority. Now that's one thing we can do with graphs. Now I'd like to talk about a second item we can play with graphs. Let me see, it's this one. This one is a little more interesting, perhaps. It's kind of a strange concept at first. The graph theorists, people, for example, Kayla McBee does good graph theory, although she's in combinatorics, but she knows graphs. I think she's in graph theory, actually. Now, the graph theorists have said, I've defined something called a coloring of a graph. A coloring says, here we have a graph. We want to put colors on each one of these nodes in such a way that if two nodes have an arc between them, they have different colors. So A and B can't have the same color. A and C can't. G and C, G and H, G and E, they all can't have the same colors. So it's relatively simple to think of how to do this. I start with A. I give it a color. I'm going to give it red. Then I can look at B, C, and D. I'm going to give all of them blue. So as I go through here, I'm going to say, okay. Now, if they're blue, and I look at E, well, it could be red. It's not adjacent to A, C, or D, so I'll make it red. Then if I look at E, well, E's adjacent to a blue, but not a red, so I'll give it a red. So far I've got 1, 2, 3 reds and 3 blues. A, E, and F are red, and B, C, and D are blue. Now I come to G. G can't be blue because it's next to C. It can't be red because it's next to E. So I have to pick a different color. I'll pick yellow. Now I go to H. H is next to D, which is red. It is next to G, which is yellow. Pardon me, D is blue. G is yellow. F is a red. We need another color. I'll pick purple. And then I do the same thing for J and I. And when I finish, there's my coloring of the graph. I used 4 colors. I couldn't get away with less. Now you might be saying, did we go to elementary school? Is this the 3rd grade? Why are we coloring graphs? Well, it turns out that this can be a very useful concept. I'm going to give an example I saw on the web, which I thought was pretty interesting. But then, I like some interesting examples. Suppose each of the ovals is a college class. And if 2 ovals are adjacent, there's at least 1 student who is in both classes. Now, unlike Providence College is set up, the college where this is has a final schedule that varies in length. Their object is to make the shortest final schedule possible, and they want no overlaps, no conflicts at all. So how is the registrar going to do this? Well, we've got a small graph. It could be huge. It could be 200 classes or something. So we need to find a way around this. It turns out that if we color the graphs, then the number of colors we use is the number of exam periods we need. And that's rather amazing in a sense, but it does work. Now, I've got a program here, but first I want to show you the data. This is my data file. I have the name of the node, like A, and then the numbers of its adjacent nodes. Now, I made a mistake when I typed it up, and I didn't want to retype it. I started it with 1s instead of 0s. So in my actual program, I subtract 1 from all of those that come in. So I'm going really from 0 to 9, not from 1 to 10. For each of the nodes, I put a done adjacency at the end of all the adjacent nodes to that one. Then when I'm finished with the entire graph, I put a done graph. Doing it this way makes it easier to read, and it went in for me without much trouble. Now, this means, for example, that A shares students with the nodes 2, 3, and 4, which are actually 1, 2, and 3. So it shares students with B, for example. I believe this is actually the graph up at the top. It might not be, but I think it is. Now, this was the output of my program. It said A had 1, 2, and 3 as its adjacencies, B, 0, 4, and 5, and so on. And then it said the coloring should be, there are 4 reds, there are 4 blues, there's 1 yellow, and 1 purple. So how did they do that? Well, as you might guess, this is going to be your last homework. I wrote up most of the program, but you're going to fill in the details. I started with telling you what kinds of structures we're going to have in the program. We're going to define a struct vertex with its adjacent vertexes. What it's going to be is it has a color, which started out as none. It has a name, and it has a vector that is all the adjacent nodes. And again, those are numbers, remember. What I'm going to do is make an array of these structures. And when I have a number like 2 in the adjacency list there, that means that that vertex is next to GR bracket 2, where GR is the list of all the vertical adjacency list. I also have an array of colors, and to make it general, I put num_c as the number of colors. I have an array called eliminated, which I'll show you the use for in a minute. An array called GR, which is the vector, is the array which has all of the nodes in it, and each node has an adjacency list. Num_v is the number of vertices. Num_next color. This is the color in my list of colors. This is the next one I would assign if I have to find another color. If I don't, I've used all the colors before this one. So I'm going to be setting that to 1 because I'm going to use color 0 to color one of the vertices. And then from there, every time I need a new color, I'm going to take the next color, the color in num_next color, and then I'm going to add 1 to it. The algorithm goes as follows. Mark the first vector, the first out vertex, 0, with color 0. Set the number of the next color to 1. Remember, that means if I have to pick another color, it's going to be color bracket 1. For each vertex that I haven't done yet, mark all colors as not eliminated. What I mean by that is you go through and you put no in each of the eliminated sections. Then, for each vertex adjacent to V, if V2 has a color C, eliminate C as a possible color. And you do that by changing the appropriate place. Now, you may have to also in here accept the color of C of V is marked no, marked yes to eliminate it. So when you finish that, oh, pardon me, I don't need that because we haven't colored it yet. I knew there was some reason I shouldn't jump when I see something like that. All right. We have found the colors of all adjacent vertices. Now, some of them will be none. That doesn't matter. That's just we ignore those. We look through the list of colors, starting at 0 and going up to wherever we are. If every color we've used so far has been eliminated because it's the color of some other one of the adjacent vertices, then we have to take the next color. And we color that node and put it in. If there is any one of them that is not eliminated, in other words, there's no adjacent matrix with that color, we'll color it with the first one we find. When we finish that, we color all the nodes. Now, I have a starter file. I have the print function and the things I define there. I have reading the graph, which I've done for you. I have outputting the graph, which is going to come right after the reading. Then you're going to do the coloring algorithm. And then after the coloring algorithm is the printing of the colors. So you'll find, when I get a chance to put all this out, you'll find a starter file and an input file for this. That is going to be your last homework, homework 27. Now, despite that, I would like to talk about one other item that is a practical use for graphs. Suppose you're working for a company that is a for-profit making company, and it needs to lay down some utility. For example, it's a cable company, and it needs to put cable lines down. And it has connections. It's seen how it could lay it out. It's seen what connections it could make. It could have a cable from A to B, a cable from A to D, a cable from B to C, a cable from D to M, D to E. But it would like to save money. So could it arrange so every single node was connected to all the others, but there were no superfluous nodes? That is, there were no nodes that you didn't need, that were redundant. Now, this may look like it's only for companies like utilities, but networks also use this. What the network does is, if I want to get a message out to everybody on the network, what lines do I send it out on? If I send it out on every line, and every time somebody gets it, they send it out on every line they have, we're going to have far too many transmissions. So instead, we create what is called a spanning tree, a minimal spanning tree. That is, we have only the aux that we need, which will connect everything, but won't have unused aux, unneeded aux. Now, in the network version, we keep those as backups. So if one of the ones in our spanning tree dies, then we have to rearrange the spanning tree. They don't have that luxury in the cables. This problem is pretty easy it's theoretically easy to talk about, but it implies a lot of loops. Basically, what you do is you read in the tree, and then we can use something called Prim's algorithm. Prim's algorithm says create two sets. The first set is all the vertices we connected so far. And the second set is all the ones we haven't put in so far. Take one of the nodes, whichever, perhaps your main office, and put it in the connected set, and put all the rest in the unconnected set. Now, while there's at least one node in the not connected set, and here's where the complication comes, you have to look at every link that connects a vertex in the connected set to a vertex in the non-connected set. So you have to look at all possibilities of getting from the connected set to the non-connected set. Is there one aux there that you can use? Find the link with the smallest cost. Then add that aux to your spanning tree. Take the vertex that is at the end of it in the non-connected set and put it in the connected set instead, and keep going. And when you finish, and there are no more nodes in the not connected set, you've got yourself a spanning tree. The picture above, I have the answer. There's the spanning tree. You can actually see where I erased some of the nodes here, so that they weren't, because they weren't needed. So that's what I want to say about graphs right now. Graphs in computer science are a very common approach to solving many, many problems. And I'm going to point out that a tree is also a graph. A tree is a special kind of graph, a one where you don't have cycles, and where if you start at one, you keep going down to get to the others. You have graphs to represent the disk files, the hierarchy of disk files, and catalog the on C, and then C colon such and such, and then C colon such and such, such and such, the hierarchy of folders. That turns out to be a graph, be representable as a graph. And there are some versions of file systems that allow a folder to be connected to two parent folders instead of only one. We only allow one in our versions because that's the way the PCs are set up. But if you look at Unix, the Unix file system does allow for multiple parents. Now, that's it for now. I'm going to be putting these out, and I'm going to be putting out the material for homework 27. I made homework 27 due fairly late in the exam week. We don't have a final, so you can look at it as you would have had to do a final, but now you only have to do a project for it. So I hope everything works out, and I will be available as usual. Just email me. I enjoy my Zoom sessions. See you later now. Bye.